Okay, so let me start. Hello, everyone. My name is Seogi Kang. I'm going to talk about accelerating the use of public geophysical data for recharging California's groundwater. And this is not just my work, this is my work, but with other team, what we call Night Accelerator team at Stanford University, and also work with a private company called CurveNote. I'm going to mention that later. One of the reasons why I'm doing it, this is the week of what they call Love Data Week. It's happening at the same week of the Valentine's Day. And the theme of this year is the data agent of change, and Love Data Week is about inspiring your community to use data to bring about changes that matter. I thought that's a cool and inspirational sentence. And I thought what I'm going to talk about today is somewhat really there's a resonance in between what the sentence is, because I'm going to talk about the public sensor data, and the problem that I want to address is the recharge in California's groundwater, which is a very serious problem in the location that I am living. And given I'm probably a very new person to probably all of you or some of you, let me introduce myself. My name is Seogi Kang. I'm a postdoctoral fellow at the Stanford Environmental Geophysics Group. I would kind of categorize myself as a computational geophysicist using various types of sensor data, ground, airborne, satellite. And I'm passionate about open science. Open science means like developing open source software, developing documentation, and publicly releasing the data as well. And my personal sort of passion, I'm interested in extracting useful information from the sensor data to advance groundwater science and management. And that's basically what I'm going to talk about today. So let's talk about groundwater. And groundwater fills in the pore space of the sediments and rocks at the subsurface. So if you zoom in a groundwater system here, and that's blue is the groundwater, which fills in the pore space. And it occupies 97% of all liquid form of fresh water. So this is a very important freshwater resources for us and other species in this world. And with the population growth and climate change, the sustainability of groundwater can be threatened because the amount of groundwater is large, but if you use more and more, that could be depleted. So that's basically the problem. And today I'm going to use Central Valley of California, where they're really suffering from this groundwater issue. So like some explanation about the Central Valley, it is the very productive farmland. And what that means, so that's the Central Valley of California. That's our Pacific Ocean. And that's the Sierra Nevada mountains. And this is the Stanford where I am located. And as you can see, a lot of blue here. Those are a whole suite of farms, very productive farmland, which uses significant amount of surface water as well as groundwater. And in between 2012 and 16, there were very severe droughts in California that with that, the groundwater sustainability in this region was really threatened. And the California government legislated what's called a Sustainable Groundwater Management Act, called SGMA. And with that, each local water agencies and community need to come up with the sustainability plan. And that shows that sort of the stress of the water in this area. So this is a very serious problem in this location, and probably in many other locations as well. So let's just think about how much water the Central Valley is losing. And it's about 3 cubic kilometers per year of groundwater. So for the past decades, we lost about 30 cubic kilometers of water, which sounds a lot, but you don't really feel it. Okay, how much water is that? So if you think about the Shasta Reservoir, one of the biggest reservoir in California, and the capacity of this reservoir is about 6 cubic kilometers. So for the past 10 years, we have lost 5 times of this Shasta Reservoir. And the problem here is somewhat simple, water in is much smaller than water out. So water out is due to the pumping of the groundwater, and water in, you can think about that as a recharge, natural recharge or artificial recharge. So the problem is simple, but solving it is not so simple, I guess. And if you actually live in this region, this groundwater sustainability is something that you can actually feel it. So these are the images, it's not taken by me, but you can actually easily see if you drive from here at the Northern California Bay Area, if you drive to LA, crossing the Central Valley, those are the sceneries that you would see. So farmers are saying, oh, there's no water for irrigation, so they're losing their jobs. And some of the farmers having like trees, like an almond trees, because there's not much water, or it's so expensive to buy the water, they are cutting their trees apart because it's not economically valuable. So those are sort of the kind of the feel of the groundwater sustainability issues in this region, which is very, very serious. So it's very clear in California, there's an urgent need for recharging California's groundwater because water out is much larger than groundwater in. And one of the promising technology is what's called flood-MAR. It's what MAR means is a managed aquifer recharge. And the idea is it's simple, like if you have a surplus of water that somehow you can capture in the reservoir or various other parts, and you can actually divert that water to various lands and then spread the water on the surface, and that water in those lands can percolate through the subsurface and hit the water table or the aquifer system in such a way it can naturally or artificially recharge the aquifer system. So, and there could be various types of lands, like could be a floodplain habitat, or it could be a fallowed field or orchard, like a farm, or it could be a specific recharge basin. So there could be various types of lands that could be used for this flood-MAR technique. And the reason why the flood-MAR is so kind of relevant in these days is it's associated with the climate change. So with the climate change, the weather in general getting more extreme. So we're getting more extreme water events like floods, right? So this is an example image of South Yuba River. So we're getting more extreme flooding events with the more intense precipitation happening in a very short time span with increased frequencies. And on the other hand, we're also getting more droughts. So the floods means like we're getting more surplus water that actually, but if you're not capturing it, it runs off and then it probably go back to the ocean. So somehow we need to capture it. But there's a drought also happening more frequently with the extreme weather. So there's a greater need to capture those water and save and then prepare for this drought period. So that's the reason why the flood-MAR is a good kind of sort of relevant technique in these days, because there will be more flood, meaning there will be more surplus water. And somehow we need to capture that and then put that into the ground aquifer system. So that's the idea of the flood-MAR. And then the key here, we need to implement flood-MAR in many places quickly because we're in a hurry. And there are many other challenges, but what I'm going to focus on is this challenge. So say you have some subsurface system composed of clays and sand and gravel. And if you pour the water here, what you really want in terms of recharge, you want to pour here and then want the water pass through, percolate through this, what we call a fast pathway composed of sand and gravel, which is a coarse-grained material. And in terms of hydraulic conductivity, clay is a barrier, but sand and gravel is a conduit of the flow. So you want to have this fast pathway that can hit the water table about 30 to 100 meters below the surface in the southern part of the Central Valley quickly. So that's the goal. But if you actually pour the water here where the clay is located, the water will probably just runs off. Or, and if you put the here, it would actually evaporate it in the subsurface. So understanding the subsurface and finding this pathway, the fast pathway, is a critical information needed for the successful flood-MAR implementation. And how do we do that? We're going to use the sensor data and what we call electromagnetic imaging technique. And I'm going to deal with the two scale. One is the basin scale using the airborne method. And the other I'm going to explain later is the local scale using the ground-based method. And what's this airborne EM technique works is, here we have a helicopter and we have a big loop, and you inject the current that'll generate the magnetic field, which will excite the subsurface system, and that'll generate the currents in the subsurface. And depending upon the electrical resistivity value, how well it resists the flow of the current, the resulting signal will be different. So you can get the signal from the subsurface, measure at this receiver location. And the beauty of this method is the speed, because it can map out a large area very fast. And typical speed, the flight speed is about 100 kilometers per hour, and you can see depth of 200 to 400 meters. So if you're using roughly about 4 to 5 kilometer line spacing and have 50K by 50K water basin area, it only takes a few days or several days to map out the entire water basin. And that's the beauty of this method. And the line spacing, as I said, it could vary from 500 meters to 10 kilometers. And the vertical resolution at the top is 3 meters, but genuinely decreasing with the depths, because of the diffusive nature of the physics. Because of this line spacing is relatively large, sometimes you may want to have a higher resolution, maybe tens of meters in lateral dimension, or less than that. Then in such a case, you can use the ground-based method, because you're getting closer to the ground, you're more sensitive to the near surface information, you can get higher resolution. So what we call TODM method is relevant for mapping farm areas, like about 100-acre size of the area. We could map that out for a few days. It's about 7 kilometers per hour speed, and you can see about 40 to 60 meter depth. And it has about 1 meter vertical resolution at the surface. And again, it decreases with depth, and line spacing is about 10 meters. So we're getting much higher lateral and vertical resolution at the near surface point. Okay, so those are the two methodology that we're going to use, and that's what we call electromagnetic or EM imaging. And both methods sees the electrical resistivity. What we hope to see is a hydrogeology, but again, like what the sensor sees is the physical properties. That's important to understand, because the target value is hydrogeology, but what we see is electrical resistivity. So for instance, let's use blue as low resistivity and red as high resistivity. On the lower resistive end, we got seawater, lots of ions that can conduct the current well. And clays, which is the barrier of the flow, has lower resistivity than conduit of the flow, like a sand and gravel. So we're genuinely looking for, if you're looking for an aquifer system or aquifer material, we're looking for a relatively higher resistivity, and the bedrock, which could act as an impermeable base of the flow, it has much higher resistivity. But the good things, it varies with the resistivity. So if you actually know the resistivity value, you can infer what is the hydrogeology of the system. Okay? But having a single resistivity value, you're somewhat limited. It's hard to distinguish for a given resistivity, what was the clays and what was the sand and gravel. So that's the general sort of the limitation or challenges that we're up against when using this electromagnetic imaging for characterizing the subsurface system. And this is what you can get. So this is the collection of both the statewide airborne EM survey from California Department of Water Resources and other airborne EM surveys collected by Stanford Environmental Geophysics Group. And what we're seeing, so at a single location, you can think of like you have a vertical resistivity profile, okay? And then we're plotting that in a three-dimensional view. And then blue, again, is the low resistivity, and red is the high resistivity. And we're seeing from the surface to about 200 to 250 meter depth. And that's what you can get out of it from airborne electromagnetic data. And this is about 230 kilometer length scale. So it's a very effective methodology to map out a large area fast. And I want to emphasize like at this part, this is the location that where we, Stanford Environmental Geophysics flew. And this it's in our recent paper. And that's what we were really targeted to map out what we call incised valley field. And it's a, I'll show you later here. And it's a at the glaciation period, there like with this glaciation, there was a really kind of like a thick and a linear valley that generated with lots of cobbles. So because it's like we're supposed to be very like a linear feature, and then it's filled with lots of like very coarse grained materials. So it could be a great recharge pathway. So suppose we have some surface exposure of this valley field, and then if you pour the water, that could be a really good connected pathway to recharge the aquifer system in the valley. And this is the resistivity map, which we averaged from surface to the 31-meter depth, which people expected to see this incised valley field. And this resistive zone, high resistivity, means like a coarse-grained material like a sand and cobalt, and that's what we were able to find. And that's sort of the power of the electromagnetic imaging. We can actually see and find this fast pathway that could be used for recharging California's groundwater. And sometimes, like if you think about this is a 40-kilometer, and the line spacing here, for instance, it could be at least several kilometers. And then if your interest of recharge is in somewhere here, having airborne EM data is not so useful. Because all we can do is probably interpolate in between, have some resistivity value, which may have really high uncertainty. In such a case, we could use the ground-based system. So the size of this survey is about 800 meter by a couple hundred meter. And this is a ground-based system towed by ATV. So this is an image that you can obtain from this towed EM survey. And like red here is large resistivity, and the blue here is the low resistivity. So this could be a good pathway, fast pathway to recharge the water. So this is an example, and it better shows the vertical resistivity profile that we're getting from this data. And so that's kind of what I have shown, what we can get from airborne EM or EM imaging data is the resistivity. But yet to kind of have to be useful for recharge site location, there are a couple other steps that we need to introduce because resistivity itself is somewhat limited because there's an uncertainty to define what is the coarse grain unit or the clay unit, or like define the sediment type or other types of rocks. So what we do, we start from resistivity. So that's the starting point of our workflow. So we assume that we have a certain way to kind of convert the observed data into a resistivity model. And then if you have some lithology wells or driller's log that has information about the sediment type of the aquifer system, then we build a relationship between resistivity and the coarse fraction. So we're assuming the binary system, fine and coarse. And then from this coarse fraction, using this coarse fraction, somehow, I'm going to explain later, we're going to build a recharge evaluation matrix, which is a 2D maps. And then user can actually use these maps to guide their decision for recharge site location. Okay, so that's the general idea. And then we're using green as a good and bad as a the red as a bad recharge. Okay, so we're going to use the two sort of matrix. The first one is the path lengths to a water table. So what that means, we're going to just calculate the shortest distance from this point to a water table. And then we're going to repeat that for every point at the surface. So at the end, what you're going to get is a 2D map. And the second one is the depth to the shallowest low K unit. So suppose the clay is the low K unit, and we're going to calculate this depth. So you can repeat that for every point at the surface. So you're going to get another map, which is the depth to the shallowest low K unit. And the way that we're doing this, so what we do once we have a coarse fraction that we've got from resistivity model, so CF here stands for coarse fraction, and then we're going to divide that to a low K unit and high K unit, and then we're going to use what we call fast marching equation or the Eichel equation to calculate the distance, shortest distance from the surface to a water table. And that's what we're doing. And for the second one, that's kind of how it looks like. So if you do a fast marching, that's the distance from the surface. So you can calculate the shortest distance from this point to a water table. So that's the basic idea. And the second one is more simple. It's just basically calculate what is the shallowest depth to the low cave. Okay. And that's kind of an example. You start from EM resistivity model that are available, and then generate a recharge map. So you can pick a certain contour value and then start narrowing down what are the good recharge area in a basin scale. Or if you have a much smaller area, then you can use this TODM data and have a map like this, and again, start kind of narrowing down what could be a good recharge location. So we're trying to guide this site location by having this function. So the basic knowledge that I have talked so far is available like through these two papers, but yet the tool is not really accessible or useful for people facing the problem, like water managers, engineers, whoever wants to do this research site location. So that's kind of our motivation to build the web application that can use this EM geophysical data, and a lot of them are publicly available, and generate to this recharge matrix at the form of maps, so that they could bring that into their GIS layer and start and guiding their decision making, and also developing educational resources, because there are a lot of technical details about what needs to be understood. So it's a two wings, but I'm focusing on the web application part today. And this is what our Sustainability Accelerator Project. It's a one-year project ending this August. So we're sort of the halfway. And it is funded by Stanford Door School. And the Accelerator Project, there are many other Accelerator projects, but we're one of the team who are funded. And the leader is the Rosemary Knight, who's my advisor. Meredith Goebel and myself are two research scientists working on this project. And Becca, she's there, and then she's a PhD student working with Rosemary, helping compiling the database and addressing other problems as well. And I want to emphasize the role of Curve Node from Rowan and Steve. So developing the web application is absolutely beyond our research project. So we definitely need some help from software side, and making a cloud platform that can run the web application. So they are really helping us. We're teaming up with the Curve Node to develop this web application. And I also want to emphasize the role of partners, because the research idea is somewhat limited, because if you don't have very practical inputs from who are really front-facing this problem, the tool that we would build is somewhat like a limited and may not be so useful for those problems who actually would use the tools. So we're really teaming up with a whole suite of local water agencies and Department of Water Resources who are really kind of interested in this problem, trying to solve the problem. So it's obviously a teamwork and community work to develop this tool that could be useful and accelerate California's groundwater recharge. And given this is the Love Data Week, I want to kind of mention about the public data that we compiled. So we compiled the EM resistivity data in the basin scale, that means airborne EM, local scale, and TODM. It was mostly provided by the Department of Water Resources. And we also, our group also collected the airborne EM data, and then we're going to make it available through our database. And there are in situ well data also collected by DWR as well as ourselves, and it includes lithology data, water table data, and water quality data. And all of this data will be publicly available data compiled into our database using Redivis, which I'm going to comment. And some numbers about our database: we got about 500,000 resistivity soundings. It means you have 500,000 locations in California that has a vertical profile of resistivity that you can see up to 200 to 300 meters. And we have about 10,000 lithology wells and 20,000 water level wells and 3,600 water quality wells. And there will be more, because DWR has not finished it yet to release all of their data set. So we will have more data set, and then we'll compile that through this open database called Redivis. And our web application is actually just launched thanks to Steve and Rowan. And if you actually go to this website, and that's like, click it and it'll start. And obviously, like I'm temporarily calling that as an EM recharge app, but the name has not determined yet. This kind of shows we're just like starting launching this web application and started playing with. So I'm going to show a pseudo demo, which I kind of videotaped. So if you click it, like if you click that recharge now, there would be sort of the scenery that you would see. I'm going to play. So you need to have an account. Like we ask very minimal information, your email and your background. Then if you hit this explore button, it'll show up this GIS layer, kind of focused on California because our data is in California. And I picked this location called Visalia. So this is the southern part of the Central Valley where they're really suffering from this groundwater issues. And they're even having the subsurface. So the groundwater issues here is very, very serious. So what I'm doing, I'm drawing a polygon. And I'm asking, so what it does, if you finish the polygon, it'll hit the database and query what are the available data set within this polygon. And then it'll take a little bit of time, but it'll show all of the AEM data, T10 data, TODM data, ecology data, water level data that intersecting this polygon. And it shows, oh, there's 1,700 lithology wells, lots of wells, and then about 400 water level wells, and there are 100 water quality wells. And that's kind of like it, and then you can actually toggle and toggle off to show whatever the survey that you want to select. Once you've done that, then like this start simulation button will be activated. So you go ahead and click it. And that'll start our cloud computing resources. So this was on just GIS layer. Now we're hitting the Google computing machine that we set it up using the Jupyter Hub. And then what it does, it actually starts setting up our environment and start downloading data from this database called Redivis. Okay, so this will take a little bit of time. So we downloaded about 20,000 rows, so 20,000 location of EM. Downloaded the thickness information. Also downloaded about 2,500, 2,600 lithology wells, about 700 water level measurements. And sometimes it's useful to have a contour data, which the DWR interpolated. So we're also providing that interpolated water level data. And once it finishes, that's sort of the kind of the first panel that you would see, which is the data review and collocation. And what it does, so as I said, resistivity is a vertical profile at a location. So what you need to do is you need to find the pair of resistivity and lithology wells to build a transformation. Because what we want is not necessarily resistivity, it's the coarse fraction. And at the end, we want to generate the recharge matrix. So that's the core of this step. And I'm just going to play. So currently it is set to 400 meter, and that's the red dots. And you can toggle, you can click and unclick it, plot it up or not, if you like. And this blue circle shows this resistivity value as a function of depth, and this shows the sediment type. Okay? So it looks like there's more coarse-grained material, there's a fine-grained material, which is the blue. And what I clicked was the show water table, and it shows the water table. So here, yellow is the deeper, and then blue is the shallower. So you can interpolate the water table, have a map, if you like. So there are a whole suite of other kind of functionality to visualize various types of data, but I'm not going through all of them. But this is an important parameter, that the collocation radius. So for 300-meter means we're just finding the pair of lithology wells and the resistivity data within 300-meter. And the statistics shows there were about 400 wells. And then it runs the transformation. So now what we're doing, we're building the relationship between resistivity and the sediment type, which we define as fines and coarses. And that's the distribution look like. And as a first order, good to check is the coarse-grained material is supposed to be more resistive than fine-grained materials. If this is flipped, that's a good sign that they're either resistivity data, or the lithology data has like there's some problems or quality is questionable. Okay, but this looks good enough. Then it does like a transformation and generate the 3D grid of the coarse fraction model as well as the resistivity model, and we provide simple visualization that you can kind of look at it. And we're actually generating not just one model but many models because there is some uncertainty when building this relationship. And this is a simple slicer that you can toggle through from surface to a depth. So you can see how the coarse fraction model is changing. So red is the coarse and blue is the finer. And you can also change the depth slice and vertical dimensions. So this is an interesting section somewhere here. And if you put like if you want to decide where do you want to recharge, this might be a great location because what I'm showing, this is the water table. So I'm just ignoring all the cells below the water table. And so there's a sort of the direct pathway. But this may not be a great location because it'll be blocked by this clay. So this is kind of the simple sort of the first order check that you can do by visualizing this 3D model. And once you've finished playing with it, you can either stop here or you can move on to the next step, actually generating the recharge matrix. We haven't got there yet in this web form. So this will like kind of show, it's not showing much, but there will be a history and there will be a function that you can download all of the information that you have generated. So that's kind of the sort of fill of our web application. And this will be kind of the recharge matrix maps that we will provide. We haven't also yet decided like what exactly the recharge matrix will be, but this is the current plan. And the first one is the integrated coarse fraction. What we do, we have a coarse fraction model in a three-dimensional space. We just vertically average or integrate from surface to the base of the water table and then provide a map like this. So here, red is a good for recharge. And the other two here is the green is for good for recharge, but the first one is the path length to the water table. So it's what is the shortest pathway from the surface to water table through that high K unit. And this is depth to the shallowest low K unit. So by combining all three maps, user can kind of guide their recharge site location. So that's kind of the plan. And so there will be like functionality that you can export this to a TIFF file or various forms that you can readily overlay with the GIS layer that you're using. And I kind of want to give a little bit of perspective. So this was the basin scale, about 60 kilometer by 60 kilometer, so the water basin area. But sometimes if you're recharging on a farm, your scale is about a couple 100 meter, or 400 meter, or 800 meter. And that's the size. So this little blue box, it's the Clarkland, name of the farm. And that's the scale that you're dealing with. And then that's in this scale, those might be a few cells. And then I'm not 100% sure, but there might be no even data close enough to that location. So that's where we need some ground-based kind of measurements using TODM, because we need more higher resolution in such a case. And that's the local scale example. So this is about the farm that we did the TODM survey. It's about 800 meter size. And not going to the detail, but those are sort of the recharge matrix maps. So the first one is the integrated coarse fraction map, and that's the path to the water table, and that's the shallowest, the depth to the shallowest low K unit. So by combining all of this, maybe this is a good location, but it might be really depends upon what are the other factors that they have. So we're providing that as a guiding information. So this is a question for the people for a front-facing problem. Where do you want to locate your research site based upon these maps? So that was it kind of for our web application and what we're doing. And I want to emphasize like sort of our design philosophy. So we're like a group of researchers and working with some software engineers from Perfect. So what we're doing, what I was doing mainly was using, we really tried to use the software tools used by researchers, it's a typo, like NumPy, SciPy, if you're using Python. And then we generated a set of Jupyter notebooks. So the way that was structured, we have 5 different Jupyter notebooks that actually can be run on your local machine. So that's what I prepared. And then what the Curve Node guide is, they put together this and then turn that into a web application. So that's kind of how we design the workflow, how I work with the Curve Node. But I think there's an important point because like, if you have that workflow set up, that actually gives you a function or potential that what researcher develops can be readily sort of developed as a production level web application. And we're also releasing all the code that we're developing through some form of open source software like PyPy. Okay. And the magic happens with the Curve Node guys. I really want to thank Rowan and Steve for joining this project and putting a lot of efforts. So as I said, what I provided was a set of research code and public database, and they are turning that into this amazing web application. And I think they're pulling out some of the pieces and make it open source such that like this process can be accelerated. So again, this app is still in development, but feel free to play with. This is the link that you can play with. And there are a couple sort of the points that I want to mention beyond this project. And the open database, it's useful for our web application, but the fact that there is geophysical data, in situ lithology data, water level data, water quality data, this could be hugely useful for a whole suite of things. So I kind of want to show a quick demo, if that's possible. So this is the Jupyter notebook that I together. And this is kind of how you can use the Redivis on a Python. And Redivis also provides an API that you can use R or other software. So what I'm going to do, I'm going to ask, Redivis, give me all of the data in the Central Valley, like all the EM resistivity data in the Central Valley, and download it. And then we're going to use the tools that we developed to sort of sort that out the resistivity information and generate the 2D map of resistivity using some simple interpolation technique. So that's what I'm doing. And I'm going to just run it, all of them. So this is the polygon, which shows the boundary of the Central Valley. And then what I'm doing here, this is like if you know the SQL, that's the SQL kind of statement. So I'm asking the query. So give me all of these columns in this table named survey location and accept all of these surveys. This is what we have acquired. So I'm just pulling out the public data collected by Department of Water Resources. And I'm downloading about 400,000 location, the resistivity profiles in less than a minute, okay? And then I also download the thickness information. And then save it as a CSV file. And this is what we developed. It's an object, that EM dataset object that reads in the CSV file and thickness file, and gives you a kind of convenient handle to pull out the resistivity information and XY location. And I use this simple inverse distance weighting to calculate the 2D map at each layer. And I use about 1,000 meter by 1,000 meter grid. And I'm going to put a little bit of better background using a TIFF file from ESRI topo map. And I'm pulling out the first layer and showing the 2D map of this is 2D. Okay. And that's how you can do it. And I kind of want to emphasize this is a $12 million worth data, but you can download all of them in your local machine and plot it out. I thought that's pretty cool. And you could actually do, if you want to see, this was from 0 to 2 meter depth, but if you want to see deeper, change to a second layer. Okay. I think it's up to 30 layers, so you can actually play with it. So it's not yet available, but we'll open this database. We'll release database at some point, and you can actually do it on your end as well. So that's the plan. So we produced this image. Okay. And there are other potentials because infill surveys, which will be interesting because the line spacing of this public DWR data is up to 4 to 10 kilometers or even more. So there could be a lot of infill surveys to fill in the gap in between the lines. There could be more airborne surveys and TODM surveys. And there will be a potential to either reprocess or reinvert because inversion I didn't mention at all. Depending upon how you do it, the result could be quite different. And you can actually implement more ancillary data into your inversion and update or improve the inversion results. So there are a lot of interesting potential. And given we have the open database, you can also plug in open source software like SimPEG, which I'm really involved in developing. This will provide an ability to reprocess and reinvert the data, okay, which I'm kind of excited. And accelerating the research knowledge into action. So if researchers can develop this research codes and public database, I think with the sort of the role of with the work of CurveNote and other people, there could be some pieces that could be available that could accelerate this process to kind of turn the research knowledge into an action or a production level web application. And that's probably more what Rowan and Steve could do, but I think I'm really excited to either contribute or see what will happen in the future. And here's our plan. Our web application will be available in a few months. Time spent, it's available, but we need to fine tune. So we're expecting about 3 months. Database will also be available through the Redivis, and Jupyter notebook that we use to create the app will be available, likely through GitHub. And developed software will be available either PyPy or GitHub. And I'm finishing up with the same sort of the inspirational sentence that Love Data we put together. Love Data is about inspiring your community to use data to bring about changes that matter. And I kind of hope that I showed sort of my inspiration to use EM geophysical data to bring about changes for recharging California's groundwater. Thank you very much. Given we don't have any moderator, so I'll get our questions to Jonathan. Oh, sorry. Oh, yeah, feel free to ask a question, unmute yourself and ask if you have any other questions.
Seogi, great talk. Thanks a lot for that. That was it was really interesting to hear about and learn what you guys are doing. I'm curious to know, I'm guessing you've already shown some of this, some previews to some of your local partners. What's their feedback? What have you heard from your local partners? Because I guess that's kind of the dream, right? Is to distribute this workflow to a broader.
It was a little bit counter intuitive because I think a lot of the local water agency, they don't really have time and power to do this, even if we provide like a simple web application. So what they asked, like they said, like they would kind of ask for consultants to do it. So they would hire third party that could do this. So I think that's sort of what we're targeting at the moment. We would kind of target this to some of the consultants that could do this job for water agencies, which seems like which we are not 100% sure how we do this, but that was the answer that we've got.
Hey, Seogi, it looks like there's some questions in the chat. So one of them is, does the method cover fractured aquifers as well?
No, it did not. So the current assumption that we used was a sedimentary aquifer system, which is the case in most of the California, as far as I understand. But I think a lot of the tools developed, I don't really see any other problem. So if you have a wells, but the interpretation would be different, but I think the developed tool still could be used. But you need to change the name from coarse to fine, like a bedrock, to the fractured part with the water saturated, I guess. So I think I don't really see any problem that this tool could be useful in such a case, but obviously you may need some modification, I guess. There is another question from Jennifer. How do you link the lithology with the resistivity? Is the user, or you already label all the data in the platform? By default, I think a user are supposed to build the transformation, because that's the reason why we're collecting all the lithology wells and water level wells or water quality wells, because by having those co-located resistivity in wells, user can build their own resistivity transform, and that transform would vary in different places. But sometimes we're planning to provide some pre-built transformation so user can actually use without building it, but the default is building by yourself. There's another question from Jason. Can the towed EM capture the unsaturated zone, including the soil as well? Can it capture thin, low permeable lake-like compacted subsoil in agricultural areas? Great question. I think there's a limitation. So there's a certain thickness for a given resistivity value of clay. There's a certain thickness that we would miss, what we call critical thickness. So this is something that you really need to play with the forest simulation or survey design. So it's not necessarily TODM will pick that up. So you better test before numerically, and then use your system to check. Another question from Gordon. What are your plans for validating your methodologies and incorporating feedback going forward? That's a really good question. To be honest, I think we don't have a very clear answer at the moment, but our plan is we'll make it available and see what the feedback would look like. And I think we're not going to make a major change, but if that's like a relatively simple change in terms of web application to modify, we would do it. Because given the limited time and money that we're putting and also working with the curve node people. Okay, I think I've addressed all of the question in the chat box. Any other questions? Okay, so if you don't have any question, thank you so much for joining this talk. I hope you enjoyed, and thanks again for coming. I was a little bit nervous that how many people would come, and I'm glad to see a lot of people came here. Thanks again so much.
Seogi, I think there's one more question in the chat box from Reese, and it's saying that surely lateral connectivity impacts recharge potential. Is this a metric in your study?
Let me see. Oh, I see. Where is that, Becca? I don't really see it.
It is it's from Reese. And
Can you read it for me? Sorry.
yeah, it says, surely lateral connectivity impacts recharge potential. Is this a metric in your study?
Yes, because I think when we're calculating that the pathway, we find the lateral pathway as well. So it's not just the vertical pathway. So we put we classify the coarse fraction with the low K and high K unit. And then if there's a low K unit, the pathway would divert, kind of will circumvent the barrier and then go down like this. So it sort of takes account. Okay. But the polluted groundwater, we're not that's not considered. So that's a great point, because actually sometimes that the coarse grained materials could contain more like a nitrate, which is one of the types of the pollutants. And we don't have a great idea at the moment, but that's definitely something that we want to consider. But it's a little bit beyond the project. All right. Thank you so much.
Thanks, Seogi. Bye.
Thanks, Ian.